Hello everyone, in this video we're going to continue our discussion about motion in one dimension. In the previous video we defined average velocity in an interval. Now we want to talk about instantaneous velocity. So if we take a typical trip that you go in the car, it doesn't have a uniform speed in one direction of motion. So you're probably stopping at the light and stop signs, slowing down at some times, speeding up at some times. So if we're talking about the average velocity of the whole trip, we're only concerned by the total time and the total initial and final position. So the average velocity of the whole trip has no information of what's happening in the middle, in between these two intervals, on the beginning of the end of this interval. However, if we divide our trip into smaller and smaller intervals, so for example, instead of going from, like the figure here, if going from 0.0 to 0.5 miles altogether, I could actually divide it into smaller intervals, from 0 to 1, from 1 to 2, from 2 to 3, etc., etc. This would give us more information about what's happening at each time. So I can actually go smaller and smaller. So instead of 1 mile intervals, I could take 0.1 miles intervals, and I could go smaller and smaller. So the shorter the time interval I have, the more information I have about the instantaneous velocity of the car at any time. Mathematically, now I can make a definition, or I can define the velocity of the car at any time t during my trip in the x direction. Again, I'm still defining the velocity in the x direction as Vx is the limit of delta x over delta t as delta t goes to 0. So I'm making my interval very, very small that it goes to 0. This is basically a definition of a derivative, if you're familiar with calculus a little bit. So it's the change of position. So the velocity is still the change of position with the change of time. But what I'm doing is I'm making my time interval very, very small that it becomes 1 point in time. So the instantaneous velocity is going to tell us how fast and in which direction the object is moving at any instant t. To better understand this, we can actually plot the graph of the position function of time. So here, if you look at figure A, what we have here on the horizontal axis, we have time. On the vertical axis, we have position x. Remember, here we're talking about only motion in one dimension. So we are only moving in the x direction. So if we take 2 points, t1 and t2, at t1, the object was at position x1, let's say, and at t2, it was at position t2. So if I define the average velocity between t1 and t2, it's going to be delta x, the change in position, over delta t, which is the change in time. This gives us the slope of this line here, connecting the initial point and the final point on my position time graph. This is called the secant line. And the average velocity is basically the slope of the secant line between the initial and the final position. Now, if I want to look at, make my velocity instantaneous, so if I will look at t1 alone, I want to know the instantaneous velocity at t1. What I have to do is I want to make my interval smaller. So I want to bring t2 closer to t1. So I'm trying to make t2 and t1 as 1 point. So I'm bringing it closer and closer. You see how this line is changing here in figure B. So here it was the initial point where I took it. Now I'm making it closer to t1. Eventually, this secant line is just going to intersect my graph at 1 point. And a line that intersects the graph as 1 point is basically the tangent of the line. So the instantaneous velocity is going to be the tangent of the slope of the tangent at the point where I want to know the velocity. So it's not ill-defined, because if we go back to the previous slide, we have delta x over delta t as time goes to 0. But both delta x and delta t goes to 0 at the same time. So it's not actually an infinite value. It is well defined, and it is the derivative of position function of time, or if we want to look at it graphically, it would be the slope of the tangent of the position versus time graph. So if the slope is parallel to the time axis, it means that time is moving, but position is not moving. So the velocity is 0 at that instant. And the steeper the tangent is, the bigger the magnitude of the velocity. If it's steep in the upward direction, it would be positive velocity. So it's the object moving in the positive direction at that moment. Now, so I'm defining it at one moment. If it was steep in the negative direction and downward like this, it means that the object is moving backward and the velocity is negative. So here is an example of how we can look at the velocity function of time. So now we're defining velocity at each moment. So it's same as we can define the position at any moment, we want to look at the velocity at any moment. So here we are given the position function of time graph, and we want to deduce how the velocity is changing function of time. Few things we need to remember is that if the velocity is positive, the object is moving forward. If the velocity is negative, the object is moving backward. Now, how the velocity is changing tell us how the curve is curving. If the velocity is 0, it means that the tangent is parallel to the time axis. Let's get the pen here. Okay, let's look at t equal to 0 here, at the initial point here. If I draw the tangent here, you see the red line is the tangent to the curve, as good as I can draw with my mouse. It's going downward. This, what does it tell me? It doesn't tell me that the velocity is increasing or decreasing. It tells me that the velocity is negative. The object is moving in the negative direction. Its position is decreasing. So actually this directly get rid of all the first three options we have, and we end up with option D. So at t equal to 0, the velocity is negative. It has to be below the time axis. It has to be negative. Now, as time goes forward, you see the slope is actually decreasing. Eventually, here at this point exactly, the tangent becomes parallel to the time axis. So it means that the particle stopped. So its velocity is 0. It doesn't mean it stopped and stays there. Stopping means it's changing direction. So it was going downward, and then it not suddenly, but eventually it starts going upward. So here the slope is positive. So you see we have a positive slope, and it's becoming steeper and steeper, so it's becoming more and more positive. So this means that the velocity is becoming positive, more and more positive. Okay? So as we move forward, the object stays more and more positive. This is an example of something, for example, if you want to think of it as an example, think of throwing something in the air and taking the positive direction downward. So the object goes up, it reaches its maximum position, and then it turns around and starts going downward, which in this case we call that as our positive x direction. Okay, we're gonna come to more examples later on that. Now let's move to define what is an acceleration. So as we saw from the previous example, that even velocity could be changing as time goes forward. So the instantaneous velocity is not the same at all the times of my duration. So we need to define the change of velocity. So the change in velocity means that we have acceleration. Whenever we say we have an acceleration, it means that we have a change in the velocity. Remember, velocity is not only a value, it's value and direction. So we have to pay attention to these two things. So we're going to define first, as we did with velocity, we're going to define the average acceleration. So the average acceleration is the change in velocity, the average acceleration in the x direction. So here we have, again, ax to indicate that here also we are talking about the acceleration in the x direction. And we have the bar here to indicate that this is an average quantity. It's the change in velocity in the, between t1 and t2, over delta t. Here we're not talking about average velocity anymore, we're talking about instantaneous velocity. The instantaneous velocity at the beginning and the end of the interval. We can also define the instantaneous acceleration. We just have to take the time interval to become 0 and 0. So if you look at the dimensions of the acceleration, it's velocity over time, and velocity is distance over time. So we got distance over time squared. So the acceleration has a dimension of distance over time squared. The standard unit of acceleration is meter per second squared. And also, acceleration has direction and magnitude. Now, the direction or the sign of the acceleration is going to tell us how the velocity is changing. Is the velocity increasing or decreasing? But we have to pay attention here. This doesn't mean it's going to tell us directly if the object is speeding up or slowing down, because the velocity itself could be positive or negative as well. So, if we draw actually the graph of velocity function of time, the average acceleration is going to be the slope of the secant connecting any 2 points on this line. Instantaneous velocity is going to be the slope of the tangent at any point on this line. We're going to take an example and we look into that in more details. Now, if the acceleration is positive, it means that the velocity is increasing. But the velocity is increasing. It could be positive and increasing, and it could be negative and increasing. So if the acceleration is positive and the velocity is positive, it means that the object is speeding up. But if the acceleration is positive and the velocity is negative, it means that the object is actually slowing down, because a negative number, like for example, let's start with, say we started with a velocity of -5 and it changed to -2. This is an increase, right? But so if I calculate delta Vx, is going to be positive, but we get closer to 0, so we are slowing down. So what we care about basically is the relation between the sign of the velocity and the sign of the acceleration. So if the velocity is we both have the same sign, it means that the object is speeding up. If the both have opposite signs, it means that the object is slowing down. If we have 0 acceleration, it means that we are moving with a constant velocity. Well, it could be the velocity 0, but we could be moving with a constant velocity. Let's look at the table here. So here we have a table that actually illustrates this. So if we have a positive velocity and the acceleration is positive, it means that we are speeding up. If the velocity is negative and the acceleration is negative, so it means that after later time, the velocity is becoming more and more negative. It's becoming bigger in magnitude, but smaller or more negative. So it means that we're speeding up, but in the negative direction. So we're moving backward and speeding up. If the velocity is positive and the acceleration is negative, it means that we are slowing down. If the velocity is negative and the acceleration is positive, it means that we are slowing down. If the velocity is negative or positive, but the acceleration is 0, it means that we have a constant velocity. Now, if we have a 0 velocity, but the acceleration is not 0, either positive or negative, it means that we are speeding up from rest, or we are changing direction. Like the example we did when we passed 0 velocity, the object didn't stay there. For a moment, it had 0 velocity, but it was changing direction. It was changing from negative to positive. The only time when the object stays at rest is when the velocity and the acceleration are 0. So here we have a set of problems. Please take some time, solve these problems, and of course, I will send you the solution afterwards. However, I want you to send me the solution of these problems to see if you are understanding what's going on or not. Please pay attention to the signs, label all the quantities that you are using, choose your directions, follow the rules that we talked about. What is the object that you are studying? Choose your reference point, choose your axes, and then start solving the problem. Thank you.